as x approaches a value. So we can see on this like simple graph y equals x of a line, we can see that as like this is a little bit like as we get closer and closer to 1, we see that our y gets closer to 1. This is a bit of a contrived example because obviously the y value is just the exact same as the x value for y equals x, but this kind of gives us an idea of like how to look at it. So we see that as we get closer to our x value in question, we narrow in on like what it approaches or like what are the y value in question. So we see like, okay, 0.5 brings us closer to 1. As we get even closer to 1, our y value gets even closer to 1, and so on and so forth. So this becomes a little bit more meaningful when we have graphs that kind of have like asymptotics and kind of approach infinity in different directions. So taking a look, like if we take a look at limits at infinity, here's kind of when it gets a little bit more interesting. So for this function, y equals x squared, or f of x equals x squared, we want to take a look at what happens as our value of x approaches infinity. So here we can see like we move 1 unit in the x, or like 1 brings us 1, 10 brings us to 100, 100 brings us to 10,000. So we can see like as this grows, as this function approaches infinity, as we like keep getting larger in the x direction, we also approach infinity in the y direction. And in fact, we approach it at a much faster rate because it's x squared. And then we can similarly see if we wanted to take a look in the negative x direction, or like as x is approaching negative infinity, our value of y is also like increasing exponentially. So these should be limit, not log. Sorry for the typo. So as the limit as x approaches negative infinity is also infinity. Here we have our table where if we're taking a look at what happens to the function e to the x as x approaches negative infinity, we can see at 0, the value of e is 1. At negative 1, it gets smaller. It looks like 0.368. And then for x equals negative 10, we're like a much smaller value. So we can see that as x approaches negative infinity, e of x is approaching 0, which we can kind of see from this graph as well. Although with the drawing tools I was working with, this doesn't look like we'd expect it to kind of keep getting closer and closer to the line. So imagine that it's doing that. So if there's like any questions about limits, feel free to throw them in the chat. The important part here is like, as we approach, like as we are changing x incrementally, how does that change the output of y? Like what is that? What is our value? What is our function approaching as x approaches a certain value? Great, and then limits are an important segue into derivatives. So I'm sure you guys have like at least heard of derivatives before. If not, no worries. So within calculus, any continuous function, here's like kind of the importance of why we should understand function. It's because it's like literally in the definition of a derivative. So in any continuous function defined in an interval, it possesses a quality called a slope. So the derivative is the slope of a function. We see that straight lines, kind of show some examples of this, tend to have constant slope. Curves have a slope that changes for different values of x. So the derivative of the function can be thought basically as the value of the slope at any value of x. So the motivation behind derivatives is, so the derivative of a function measures how fast that function is growing. It gives the rate of change of a function. So other ways to think about it, or like other things that it's been called, is the derivative gives the slope of a tangent line at a certain point. So here, if we have this curve, we choose any point and then we draw a line like through that point that's like tangent, like touching only that point on that graph, then the slope of that line is also equal to the derivative of that point. And then we can also recall that the equation for a line is rise over run equals like y2 minus y1 over x2 minus x1. So we can approximate the slope of this tangent line using the point on the graph we're trying to evaluate and one infinitesimally close to that point. So in order to get the slope of this line, the tangent line, we can imagine we're taking kind of 2 points on the graph and finding the slope between those two and moving that second point closer and closer and closer until it's like we're virtually just being able to find the slope of the tangent line. So I see a question in the chat. Do imaginary numbers play any role in machine learning? That's a great question. Imaginary numbers kind of sneak up in a lot of ways in math that we don't always like realize on a first pass. I'm blanking on explicitly right now how imaginary numbers are relevant. On our next break, I'll do a little bit more digging and I'll come back with a better answer for you. But like, I wouldn't be surprised if there were some application. I mean, even just in like solving for like roots in a quadratic equation, which is sometimes useful for like figuring out how to graph and what's going on. Like imaginary numbers could play a role there. Square root of negative. Like I'll get back to you with a better answer, but my first guess is, or my first pass is like we'll have a whole section on optimization and talking about that. So yeah, that could be an application. I will dig into that a little bit more and get you a better answer there. For now, I'm going to move on. So this brings us into the formal definition of a derivative, which directly uses limits, which kind of is why we looked at limits just before. So as I mentioned, what we're doing is, and I'll show a graphic or like an image that demonstrates this better, but essentially what a derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. So this is the equation for slope. So what we're trying to do is take 2 points of the graph where x is the point in question. And like as we move h closer and closer to that point, figure out the slope of that line, which essentially gives us the slope of the tangent line. So here we have the definition of a derivative right here. And then we have like this graph here. So suppose this is the point whose derivative we're trying to find. In order to find the slope of this graph, it's blue. So in order to find the slope of this graph, here we have our point f of x and then f of x plus h. And then here, so our total height right now is h. So what we're finding is the slope of the line, like rise over run. And then as we move this point closer and closer, then we can see that like the original line looks like, the original line like links these 2 points. So it's not quite the tangent line. If we had a guy here, it gets slightly closer. Drawing straight lines is hard here. And then if we have like 2 points right here, then that looks a lot more like the slope of the tangent line. So as we decrease that value of h, then we like have a better approximation of the value of that line. So with that being said, I see another comment in the Q&A saying that the derivative of a function can also show how fast the function is slowing too. Yeah, absolutely. It shows like the rate at which it's increasing or decreasing. And we'll look at optimization, whether that, like when we talk about optimization, like whether it's increasing or decreasing or whether it changes from increasing to decreasing kind of is something we can learn from derivatives and helps us find like max and min values. So absolutely. So hopefully this isn't too confusing. What we're doing is we're essentially just trying to find, like, take any point on the graph and find the slope of that tangent line. So, like, with that being said, there's a few rules so that you don't always have to apply that whole limits function. We have like some basic rules that kind of govern how to take derivatives. So the most basic rules are that the derivative of a constant is 0. We see that it's a horizontal line, so the slope of any point on that line is also a horizontal line. And so the slope's not changing at all, so the derivative is 0. The slope of like any line is just defined by the slope of that line, which makes sense. And then the derivative of x to the n, and we're not going to go through the derivation of this, but essentially what you do is you pull the n out front, and then you raise x to the n minus 1. And then the derivative of a raised to the power x is just equal to a to the x times the natural log of a. So this kind of comes up with, like, if we're taking the derivative of e to the x, if we remember properties of derivatives, ln, the natural log, is just the log base e of x. So if we take the log base e of e, and that cancels out, we're just left with 1. So that's why the derivative of e to the x is just e to the x. And we'll see that, I think, in some examples. So in addition to those basic rules, there's also some more advanced rules for computing derivatives. We have the constant multiple rule, where we just take the derivative of, if DL saying the magic of E, absolutely. Very awesome number. Constant multiple rule, if we're taking the derivative of a constant times a function, we can just pull that constant out front, and it's just equal to the derivative of that function. So if this notation is confusing, f prime means like the derivative of the function f, which is the same as d over dx of f, which is the same as like df over dx. So my notation might change kind of throughout. Those are the three common ways to represent like derivatives. So the sum difference rule, if we have d over dx of f plus or minus g, then that's equal to the derivative of f plus or minus the derivative of g. Remember that addition's commutative, so we can go, associative, but it's commutative, so we could do, like, this works for f plus g could equal g prime plus f prime. For subtraction, we can't, like, switch the order. Product rule gets a little bit trickier. Oops, looks like I have a typo in quotient rule. I'll write that up on the whiteboard, but we'll get there in a second. So product rule, if you have f times g, so two functions multiplied by each other, then you just take the derivative of one function times the other function plus the derivative of that first function, the first function times the derivative of the second. And you could like swap the order of these two because addition is commutative. So, and multiplication is commutative. So let me write up the quotient rule. So if we are dealing with the quotient, so we have d over dx of like one function divided by another function, where f and g are both functions, continuous function defined in an interval, then this is equal to the derivative of f times the derivative of g minus f times the derivative of g all over the actual function g squared. And this is derived just from that the definition of a derivative that we saw before. We're not going to go through that in this course. So that's what we mean by the quotient rule. And then before we go into an exercise, I also just want to, we can do a few examples together, and then I will send you guys on your own to take some derivatives to work through those exercises that I'll put up for you in a second. So based on the rules that we saw before, let me pull up that the derivatives for basic functions sheet. We saw that the derivative of x raised to the nth power is just equal to, first move the n out front, so n times x raised to the n minus 1. So first we move that 2 out front, and then we multiply that by x raised to the 2 minus 1. So what we're left with is 2x. For this guy, we just have to apply a series of different operations. This uses the constant multiple rule and this sum difference rule. So we can see, first we can tackle this guy. We can keep the 6 as is. And then we want to move that 4 out front. And then we take x to the 4 minus 1, which is 3. and then we can just add this to the derivative of this term. So we'll keep the x as is, so it'll be 8 times 3 times x to the 3 minus 1, which is 2. And then we can once again just add it to the derivative of this guy. So this is 12 times 2 times x to the 2 minus 1, which is 1. So then what we're left with is these all conveniently equal 24. So I'm just going to pull out 24. This is 24 times x cubed plus x squared plus x. So here's an example of kind of applying a few of the different rules. And then last but not least, we have 2e to the x. So once again, we just keep 2 out front. And then here, the typical rule is a to the x times the natural log of a. So here we'll do that in the same order. So e to the x times the natural log of e, as I mentioned, and as DL pointed out, due to the magic nature of e, this just equals 1. And so then we're just left with 2e to the x. So here's some example of taking a few derivatives. If this is scary to anyone, no worries. All it is just applying a series of rules. So hopefully you can look through the slides. I'm going to put up a few exercise problems where I'm going to give you guys like 5 minutes to practice taking the derivatives. And then after this, we'll go over them. We'll take a quick 5-minute break, and then we'll move on to talking about partial derivatives. Then we raise x to the 2 minus 1, which is equal to 1. So we're left with 6x. Here, we can see that the constant in front of each of these is just a 1. So we're just keeping the 1. And then for x to the 5th, we know we move the 5 out front. This is 5 times x to the 5 minus 1, which is x fourth, plus move the 3 out front, and then raise x to the 3 minus 1, which is just x squared. And then last but not least, so we know that the slope of just a value x is equal to, it's like the slope of that line. So this is just like the line y equals x. So we know that its slope is 1. Another way to look at this is we can apply that same rule where we move n out front. So we know that we have x raised to the 1. So we can move the 1 out front times x to the 1 minus 1, which is equal to 0, which is just equal to 1. So nice to see that that rule still applies. And then last but not least, here we have to use our product rule. So just remembering this, d over dx of f times g is just equal to f prime g plus f g prime. So in this case, this is our f and this is our g. So first we can take the derivative of x squared, which we see is just 2x. So we have 2x times 2 to the x, since we leave g intact, plus now we leave our f intact, so we have x squared. For sanity, I'm going to add in some parentheses. Plus x squared times the derivative of this guy. So we saw before, it is just equal to 2 to the x times the natural log of a, where 2 is our a in this case. So we're left with that guy. If anyone has any questions about how we did any of these or what rules we used, feel free to throw that in the chat. I also looked into DL's question, where like how are imaginary numbers used in machine learning. What I mostly saw was kind of two things. One, for like signal processing, which is used in like natural language recognition systems or other things. They use like a Fourier transform, which sometimes uses complex numbers. So that's kind of one case. Or if you're working in like on some kind of like electrical engineering or physics application where there's already like complex numbers in question, then like as you're just like predicting values or like feeding in values, then some of those might involve complex numbers. So that's an interesting question. If anyone else has other perspectives, always love to learn during these courses as well. So during these trainings as well. So with that being said, I'm going to send out a 5-minute break timer. When we get back, we'll talk briefly, like I mentioned, partial derivatives, go into optimization, integrals.